गणेशाय नमः, सरस्वत्यै नमः, श्रीगुरुभ्यो नमः, हरिः ओम्। जातवेदसे सुनवामसो ममराति यतो निदहाति वेदः, स नः पर्षदति दुर्गाणि विश्वानावेव सिन्धुं दुरितात्यग्निः, तामग्निवर्णां तपसा ज्वलन्तीं वैरोचनीं कर्मफलेषु जुष्टाम् दुर्गां देवीगुं शरणमहं प्रपद्ये, सुतरसि तरसे नमः। अग्ने त्वं पारयानव्यो अस्मान् स्वस्तिभिरति दुर्गाणि विश्वा, पूश्च पृथ्वी बहुला न उर्वी भवातोकायतनयाय संयोः, विश्वानि नो दुर्गः जातवेदः सिन्धुन्ननावादुरिताति पर्षीम्, अग्ने अत्रिवन्मनसा गृणानोऽस्माकं भोज्यभिता तनूनाम्, पृतनाजितगुं सहमानमुग्रमग्निगुं हुवेम परमात्सधस्तात्, स नः पर्षदति दुर्गाणि विश्वाक्षामद्देवो अतिदुरितात्यग्निः, प्रत्नोषि कमीढ्यो अध्वरेषु सनाच्च होता नव्यस्य सत्सि, स्वाञ्चाग्ने तनुवं विप्रयस्वास्मभ्यं च सौभगमायजस्व, गोभिर्जुष्टमयुजो निषिक्तन्तवेन्द्र विष्णोरनुसञ्चरेमा, नाकस्य पृष्ठमभि संवसा नो वैष्णवीं लोक इह मादयन्ताम्, कात्यायनाय विद्महे कन्याकुमारि धीमहि तन्नो दुर्गिः प्रचोदयात्। ओम शांति शांति शांति।
Good morning, everyone. Welcome to the second day of the workshop. It's a pleasure and honor to introduce the first keynote address for the day, Professor Luis Grillo. He's an adjunct professor at the Polytechnic Institute of Tomar in Portugal. He's also a director of surveys and statistical studies at Center for Polytechnic Institute of Tomar, and he has been organizing a number of workshops in Europe and a well-known statistician around the world. He has, as an integrated member of the Center for Mathematics and Application of the Faculty of Science and Technology of the New University of Lisbon, he has developed scientific research in distribution theory and applied statistics. Currently, he is also collaborating member of the Smart City Research Center of the Polytechnic Institute of Tomar and in the Center for Innovation and Research in Business Science and Information Systems of the Polytechnic Institute of Porto, Portugal. By the way, in Portugal, there are two types of systems. One is the university system as well as as well as the polytechnic system. Both are higher educational, and he is part of this Polytechnic Institute system. He regularly publishes papers in international scientific journal and has made several presentations in national and international scientific meetings. And we have been kind enough that he has accepted our invitation to come here and be part of this workshop. So please welcome me for graciously asking him to come on the stage and give the keynote address.
So, good morning to all of you. Allow me to start by thanking to all the members of the organizing committee of this workshop for the opportunity to participate in this workshop for the first time. Is my first time in India, and I'm very pleased to be here. And a special thanks to Professor Anush Mubhai for this opportunity, and also to Professor Krishna Vamsi, I think it's not here, from this beautiful institution. And I also want to congratulate Professor Anush for the great job that you are doing in Arizona State University, and to bring the concept that you have in your university for this workshop, to put researchers from different fields working together. It's a great idea. So I also want to congratulate all the members of the mathematical department and computer science from this institution. I think you are doing a great job. This workshop is very well organized, and I also want to congratulate the students. I'm very impressed with your behavior and your interest to learn. I wish you the best of luck for your future life. And well, because it's my first time in India, allow me to show you just 2 or 3 slides about my institution and my city, okay, in Portugal. So I work in this campus in the city of Tomar, which is located right in the middle of Portugal. And the city of Tomar is it's a small city, but it's a historical city, also with some interesting monuments to see. One of them is the Christus Convent, which is a nice place to visit. In fact, in 2013, the Guardian elected the Convent of Christus in Tomar as the most spectacular place to visit in Portugal. Founded by the Knights Templar, it's a beautiful, mysterious, and magical place, wonderful to discover and enjoy. In fact, every year we have some festivities about the history of the city. We also organize every year in my institution, or almost every year, international conferences. In fact, we start in 2006 to organize important international conference where the Professor Rao is invited to receive an honoris causa doctorate degree. So next year, we also are going to organize an interesting conference, not in Tomar, but in the city of Covilhã, which is a city more close to Spain, more far from the sea, okay, in the east of Portugal. But we can go by highway from Tomar to Covilhã, and 3 hours after we are in Covilhã. So, and I would like to invite you to participate in this conference. It will be a pleasure to have you in this meeting. So I can share the slides if you want with you at the end, and you can see the address and the links, okay? So the conference is, it will be at the end of June, as you can see here, okay? But I'm here to talk about structural equation modeling, which is a multivariate technique, statistical multivariate technique that we can use, for example, in the social science, health science. And I'm going to use a case study to introduce you to show you this technique, this statistical technique. So let's see if I can talk about all these points that I have here. And I have prepared a few slides to help me to show you, to introduce you to this subject. So as you probably know, the number of workers exposed to psychosocial stressors has been increasing through the age in every activity sectors, with negative consequences for workers, organization, and national economies, which assessment may bring benefits for them all. The warning signs include emotional changes, behavioral changes, cognitive issues, and physical and mental ill health. One of the occupational or professional diseases, which is considered the end of the line, is the burnout syndrome or burnout state. Okay? Burnout is a state of emotional, mental, and physical exhaustion caused by excessive and prolonged stress, or I should say distress, because there is a difference between distress, which is referred to a negative stress, and eustress, which is a term for positive stress. I hope I'm feeling now eustress here in front of you. I'm in eustress, okay? That helped me to talk with you. Okay. Burnout state is also characterized by disengagement, loss of motivation, ideals, and hope. And you can find more details about this professional disease for example, in the references on the bottom of this slide. So, but there is some important difference between stress and burnout. And we just can read the sentence below this table that resumes the table, because stress, people can still imagine that if they can get everything under control, they will feel better. And burnout occurs when you feel overwhelmed and unable to meet constant demands. So in Portugal, and according to a study developed in 2015, where several activity sectors were considered, the percentage of workers in burnout state surpassed 70%, when normally it should be between 7 and 9%. We are close to the percentage of the other countries in members to the European Union. In fact, 20% of workers in European Union have their health at risk because of work-related stress. So that's why it's so important to study this syndrome, to identify the possible causes and symptoms in order to help the medical community to treat this mental disturb. So in this case study, they used the Copenhagen psychosocial questionnaire, which is an international and validated questionnaire to assess the psychosocial risks. And we use a short Portuguese version of this questionnaire to assess the psychosocial risks and their impacts on workers' health and well-being from a service company. Some of the questions that are available in this questionnaire, in the COPSOC questionnaire, are here in this table. For example, about quantitative demands. Is your workload accumulating because it is poorly distributed? How often do not have time to complete all the tasks of your job? And for example, about work-family conflicts. Do you feel that your work drains so much of your energy that it has a negative effect on your private life? For example, about burnout. Are you physically exhausted? Are you emotionally exhausted? So as you can see, we have a correspondence between these questions and the latent variables or latent constructs that we cannot measure, because a latent variable that we have here in the first column of this table, we can't measure directly, but we can measure, well, in some sense, using these questions, these latent variables that we have here, because according to the experts on this field, they are related, okay? So in the second column, we have the abbreviations that we used for these variables, for questions, if you want, which is the manifest questions or indicators, observed variables. All these terms are similar, okay? We can use them. So, and here we have the indicators. So we use a Likert type scale to measure these variables with 5 categories. So we have here qualitative variables with 5 ordinal categories. Okay. At this point, I have to say that I didn't have any intervention of the procedure to get the data, okay? And I'm saying this because many times some colleagues came to me, in this case a doctor for occupational health, came to me with a data set, with a matrix, and asked me, can you help me with this situation, with this data, with this questionnaire? I would like to analyze which variables are more important to the explanation of burnout state. And I always remember the card that Ronald Fisher had in the hall of his office. When someone consults a statistician asking for the analysis of the data collected without his prior advices, he wants a diagnosis, but in general, it is only possible to do an autopsy. It's the problem that we have many times. So the data, just a part of the matrix is here. And in this case, we have, well, I don't know if I can say a big data, but we have 41 variables, which corresponds to the columns of this matrix. And we have around 5,000 observations, 5,000 lines, which is a good sample, very representative. Well, this data is confidential. I can share with you, but it's from a company, Services, from Portugal, and I think I can say it's from the most important bank in Portugal. Okay, this bank has around 8,000 workers spread for all country. Okay. So let's focus in what we want to study. Here are some of the latent variables that we can consider in this study. Not all of them, of course, because I don't have space to put all of them. But the interesting in these models is we can use some priorly acknowledge to design the model. Okay, so we can use some information from the specialized literature, also some empirical knowledge from the doctors, from the psychologists, and this way we can start to construct the model using this information. And then we'll see what the data said, okay, about the estimation of the model. So this SEM, it's interesting because it is possible to incorporate unobservable variables measured indirectly by the constructors, and then analyze the relationship among the indicators and constructors, as well between the latent variables. So SEM is considered one of the most powerful and useful advanced multivariate statistical analysis, combining aspects of both factors analysis and regression, factor analysis and regression. So it's not necessary a huge background in statistics to use this technique, this software. Of course, we need some information about inference statistics, like confidence intervals, hypothesis tests, and regression, linear regression. Of course, because we are in the field of multivariate analysis, it is a good idea that we know what is a covariance variance matrix and correlation matrix and things like that. So in this case, we have 5 categories, and because this case is perceived as symmetric and equidistant, it will behave as an interval scale, or can be approximated to an interval level measurement. So in this case, according to the Professor Joe Hare, which is one of the authors of the book in the bottom of the slide, we can apply the SEM in this situation. Joe Hare is a professor from US. In fact, I met him a few weeks ago in Portugal. And he is very well known, not because of this book, but because of the multivariate analysis that he wrote in the past. So let's try to focus again. What is the main purpose of our work? Having in mind to build a model based on workers' perception about their occupational health. Implicitly in their answers, the SEM method was applied to estimate the cause-effect relationship model with the latent variables. And some of the objectives are here. So we would like to know which variables cause stress and work-family conflicts on workers. Has occupational stress a positive impact on worker-family conflicts or not? Are occupational stress and work-family conflict predictors of the worker's burnout state? And we can express these questions statistically in hypotheses, for example, like here in this slide. Okay, stress has or not a significant influence on work-family conflicts. Stress has or not a significant influence on burnout, things like that. So why we decided to use the partial least square to estimate the SEM? Because we can think to use, for example, a covariance-based method like maximum likelihood method to estimate the model. But I decided to use the partial least square because many times in social science and as well as in health science, it's common to have data which do not adhere to a normal multivariate distribution. It's very difficult to have empirical data with normal distribution. because it's not just a normal distribution. It's a normal multivariate distribution. And we also have a complex model to design. Large number of indicators, large number of latent variables, and it's difficult to obtain a model for this situation. And in this case, in this particular case, we have a good sample, a very representative sample. But sometimes the number of cases is less than the number of variables. We can use the partial least square in this case. But we cannot use the maximum likelihood methods to estimate the methods. Because this SEM is a non-parametric method. Okay? So, and we also have ordinal qualitative variables, which is also an important issue. So, in this particular situation, I think it's PLS algorithm is particularly recommended. So let's consider a model like this, using some prior knowledge, some information for the doctors, psychologists. According to them, we construct a model like this. Burnout is the end of the line. It's the dependent variable or endogenous variable. And we have here 4 exogenous or independent variables that are predictors of stress and work-family conflicts. And both of them are predictors of burnout. If you don't mind, I would like to show you how to work with smart PLES to obtain this model. It's very easy.
So the objective questions that you had, related to this. The 3 questions that you had in the objective, does stress and work family correspond to burnout? So those questions seem to be straight leading to this diagram. Was the diagram created first and then the questions, or the questions led to this model here?
Let me show you in the smart PLES. Okay. Maybe I answer you to the question.
Yeah.
Okay. Well, smart PLES first of all, let me give you this information about the softwares. Smart PLES 3, it's not free, unfortunately. But the version 2.0 is free. And we also have here some books. For example, the first book is available in the internet. And if you want to use the software free, you can use also the PLES path modeling with the project, the HAR project, in the HAR software. Okay? And in this case, I advise you to follow this author, Gaston Sanchez from Spain. It's also a professor in the US. The quality of his work is wonderful. Okay, and this book is available also in the internet. In fact, all the work that he is doing is available in the internet. And well, in this case, I'm going to use the version 3 because I have this software here. And first, to use the data, we have to format the data in Excel with the extension CSVs, which is the separate values, the common separate values. And then it's very easy because we are here in a Windows environment. You know, everything is easier to do. And imagine that we want to create a new project, a new pass model. For example, new I should say Department of Mathematics and Computational Science. Okay, something like this. Well, I have here a new page, and now on your left-hand side, we have here the indicators. And for example, we are going to consider the burnout, the end of the line. So we can fix here these two variables and drag and drop. Okay. Then we should rename the latent variable with burnout. That's okay. Let's align the indicators to the right and from here. And now a stress, drag, drop, and I'm just going to do this for these three variables. Working family conflicts. And so these three latent variables with the correspondent indicators are a model, a simple model. The measurement model, that's the name of this model, because the latent variables are not linked yet, okay? But now I'm going to link these latent variables. I just have to click here, connect it, and imagine that the occupational doctors are interested to test if the stress explain the work-families conflicts, and if both of them explain burnout. Okay? And now I have this structural model here because they are blue, as you can see. And but now one of the questions is, which are the variables that explain the variance of the stress and work-families conflicts? And now we can put more latent variables here and link them. Imagine that we want to create this model. Now I want to estimate the model. And I'm going to use the PLES algorithm, a consistent PLES algorithm, because here we have a reflected model. We can also have a formative model, but in this case we have a reflected model because the arrows are from the latent variables to the indicators and not the other way around. Okay? But to analyze the model, to analyze the adjusted model, let me run here. Of course, here we have some settings that we have to analyze. But all the information are on your right here about the settings that we should consider. Of course, in many papers, books, there are some guides that we can use to create our model, namely questions about which algorithm we should use to end with the missing data, and things like that. But imagine that by default everything is okay, and run the algorithm. So here we have the correlations between indicators and latent variables. We just have correlations. And between latent variables, we have the beta parameters of a linear regression. So it's a simple technique, very good for the doctors to understand this technique. In the beginning, I started to use some regression models, like multinomial regression models, ordinal regression models. But some of them told me, well, if you can use a simple technique that we can understand better, it's, now let me show you again important slides. To evaluate the measurement model, we should take in consideration these steps. Okay, it's an algorithm that we should consider. Step by step, we should analyze the outer loadings, which is related to the size and the significance of the parameters, the composite reliability, which is related to the internal consistency, average variance extracted, which is related to the convergent validity. And we also have to analyze the discriminant validity with this recent statistic measure that is discovered to analyze the discriminant validity. And then, if the model respects all these assumptions, we should move for the evaluation of the structural model, where we also have 4 steps that we should analyze. Okay? And here are more similar with what we normally do with a linear regression. We should analyze the significance of the pass coefficient, which are in this case our beta parameters. And we should analyze the R-square, which is the values that appear inside of the latent variables. Let me show again. You see here these dependent variables, just the dependent variables. Just in the dependent variables, we have the R-square. The other variables are independent. They explain the variance of the endogenous variables. And so, of course, because I know in my mind all these steps, I can look for these numbers, and I know, for example, that I should remove this pass because the coefficient is 0.019 and should be at least 0.2. Otherwise, when I run the bootstrapping, because we should use a resampling technique to analyze the significance of the model, because we can use the framework of the classical inference statistics, because we don't have a normal distribution. We should use the bootstrapping or jackknife, for example, to do statistical inference. So I know we should remove this pass between cognitive demands and stress. And then I run the algorithm, and then I analyze again all the steps, and so on. So let's return here, because I already do this work. Okay. So here we have the estimated model. And now we can talk a little bit about the model that we obtain. So below the model, we have the equations that we can write according to the model that we obtained. And here we should analyze the different effects that we have. For example, we have a direct effect from quantitative demands to work family. But we also have an indirect effect that goes through stress to work family conflicts. So we have a direct effect and an indirect effect that goes through stress to work family conflicts. Okay? And we can obtain the value of this indirect effect just multiplying the coefficients, this coefficient by this coefficient here. And of course, burnout has two direct effects through stress and work family, and also indirect effects caused by quantitative demands. And we can express these indirect effects doing this. Is a simple system of equations. Okay? Of course, if the model is everything is correct, everything is fine, we should analyze also the magnitude of the values of our coefficients, the estimated coefficients, because they are standardized and we can compare with each other, all the coefficients. For example, the quantitative demands have more explanation to the stress than the work-family conflicts, and stress has an important contribution to the burnout, as you can see here. And we should analyze also the signal of each coefficient. In this case, we have positive coefficient because when we have more quantitative demands, we have more stress, we have more work-family conflicts, and okay, things like this. So about the bootstrap, I don't know if all of you are familiarized with this procedure, but for example, sometimes some colleagues of mine ask me, well, I don't understand very well this procedure, because using this program, for example, we just see the outputs. But sometimes I use the Excel to show them how to obtain how to use the bootstrap, okay, to obtain lots of samples. For example, according to hair, we should use 5,000 subsamples. Normally in the Excel, I use 1,000 subsamples because we need to have 1,000 lines, okay, in the Excel, and then to get all the statistics that we need. So, but here we can put 5,000 or 10,000. We just have to wait a few minutes because it's a procedure that needs some time to run. And then we can obtain T statistics, P values, 95% confidence intervals for our coefficients, and for all statistics that we need to analyze the quality of the adjustment. Okay? So let's skip that slide. Here we have the results that we obtained for the measurement model. Everything is okay with that model. Okay, as you can see, just look to the p-values. Okay, all of them are approximately 0, and we reject the null hypothesis of the parameters are equal to 0, things like that. So also about structural model is everything is okay. I don't have time to explain you the effect size, F square and chi square, which is the predictive relevance, which is a measure of that we can use is used normally to analyze the goodness of fit. Okay, this measure here is also a recent measure that we can apply to analyze the goodness of fit of the model that we obtained. So let me talk about some conclusions. I think I just call your attention, especially for the last point. Okay. Although the socio-demographic variables that characterize the workers, such as gender, age, and educational level, were not available, the results obtained are considered of great importance for the prevention players who champion the protection of the workers' health, avoiding bad work atmosphere, poor social relationship, and absenteeism, since this entails huge costs in terms of human suffering, as well as a decline in economic performance. I would like to say another thing about the burnout state and the stress. At the moment, I'm also collaborating with Professor Mubai in Arizona State University with a study similar to this one, because also the students suffer from stress and burnout in some situations during the student life in different periods of the time. And we are interested to establish some relationship or to analyze some relationship between, for example, stress and GPA, stress and alcoholic habits, things like that. Okay, and I think it's also an interesting study. But I know all the models are wrong, and here I prefer to use this sentence of Taki. Okay, an approximation answer to the right problems is worth a good deal more than an exact answer to the approximate problem. I know we just have an approximation here. It's just a model of the reality. It's not the reality, of course. And nowadays, some institutions are using preventive solutions to create a good psychosocial work environment. And of course, we all prefer preventive solution instead of a treatment, because in a treatment we never know. We never know if we are taking the right medicine, the right dose. I'm saying this because I don't know if you read this information in a journal. A new study has revealed that the amount of aspirin, which is a well-known medicine, that sometimes we need to take, should depend on our body size. And too little, and you may not see any benefits, while too much, and you may causing more harm than good. This paper is published last month in this well-known journal. Okay? And of course, we also have alternative approaches. And I want to close my talk with this slide and with this case that I read in one of the books of Deepak Chopra. One day a man went to an appointment at the Pak Shopper Center because he suffered from several pathologies. After a long consultation, not with the machine, okay, just observation, the Ayurvedic doctor did not prescribe any medication. Instead, the prescription consists of advising the patient to change his job, since he was a waiter in a busy restaurant and it was very difficult for him to manage the work-related stress. He decided to leave the restaurant and began to work with the computer in a new job, and 1 year later the man returned to the Deepak Shopper Center and all the symptoms had disappeared. Well, I think I don't have time to more comments, but we all understand the message. Well, here I have some references, and thank you so much for your time and for listening.
Thank you, Professor Grillo.
So if you have some questions, feel free to ask me, please.
We can have one question, I think.
So, a very, very nice talk. I wanted to know at what point do those numbers mean something to the doctors? Are you, so at what point are you helping them? Are you interpreting those numbers for them, or they, after a certain point, you just...
numbers? The coefficients?
The final, after you...
Final model?
The analysis...
No.
Where do the doctors come?
Normally the doctors, they know what is the linear regression model. Yes, they know. In Portugal, at the moment, they just have one discipline related to statistics, which is the biostatistics discipline. And also epidemiology, which is very related to statistics. But, well, the doctors normally is the best students that we have. And they are good students in mathematics also, and okay. So if they want, they understand everything. If they want to spend some time to studying, of course. But in this case, Pearson coefficient correlations, it's very easy for them to understand, and also the parameters of a linear regression is also easy to understand. Yeah. Thank you.
I think with the interest of time, we'll stop here. Thank you, Professor Grillo, for this lovely talk.
Okay, thank you.
We thank Professor Grillo for his talk. Sir, please, a token of love, sir.
Om Shri Sai Ram. My pranams at Lotus Feet of Swami. It's always a great pleasure to introduce a dear friend and a colleague. Today I'm here to introduce the next keynote speaker, Dr. Vamsi. Dr. Vamsi did his Master of Science in Mathematics, Master of Philosophy in Mathematics, and his PhD in Mathematics from Sri Sathya Sai Institute of Higher Learning, Prashant Nilayam. For his doctoral thesis, he worked on applications of timescales to singular interface problems. He published in reputed journals. He also was a recipient of the Best Presentation Award at the National Meet of Research Scholars in Mathematics and Statistics at the IIT Kanpur In 2009, he was also the recipient of 2 Young Scientist Awards, one from the KV Rao Society of Andhra Pradesh and from the AP Academy of Sciences. I will not now stand in between you and Dr. Vamsi's speech. I invite Dr. Vamsi to come over here and deliver his keynote speech.
With humility and love, I offer myself at Swami's Lotus Feet. Respected Professor Carlos, Anuj, Professor Seshar, respected elders, ladies and gentlemen, and dear brothers. So I'm really happy and excited to be here and sharing some of my research works. So the title for this talk is Modeling Patterns as Observed in Nature with reference to additional food provided predator-prey systems. So this work initially, it just started maybe a few years back, and finally we usually say that it's by the grace of God. It got published in 2 journals recently in 2018, one in Journal of Theoretical Biology, which is an Elsevier publication, and the second work is in Differential Equations and Dynamical Systems, published by the Springer. So I will be more or less speaking about the work which I have done with my earlier student Aditya, and also one of our collaborators, PD and Srinivasu. And regarding this paper, presently my student who is working under me will speak to you in the afternoon, maybe for 15 or 20 minutes or so. So now a brief outline of what I am going to speak is just as we have been telling from yesterday or maybe few days, the problem what we do actually should have a good justification, or why we are doing this problem. We should have a clear idea of what motivates us. First thing is, what are the qualitative features? I keep telling my students, maybe this may be a kind of a class rather than a presentation, because I see a lot of my students here. So it's like you observe qualitatively. But what do you do in mathematics? You quantify whatever you have observed in nature. So I want to put this at a level where actually how do we come to the model? A lot of us know once we get to the model what we can do. What are the qualitative studies we can do? But how do we come to the model? What are the different things in nature that actually motivates us to come to the model? So I will initially discuss about the motivations, of course, and what is the initial system. And then what we do is we provide an additional food, or also called as a supplement food or an alternate food to the initial model. And we see some very interesting dynamics happening in this case. It's not moving. You can just go to the next slide. Yeah, right. So what is the first interesting observation that I see is, of course, we see a lot of animals feeding on other animals, which we usually call as a predator feeding on a prey. And theoretically, not practically, theoretically what we observe is that the predators, when the prey are there, actually they are ideally supposed to exhaust all the prey, because that is the nature of the predator, which will not happen in reality. So there is a kind of a interaction happening between predator and prey, which we try to understand in the mathematical terms. So what happens is, some part of the time, what happens when the predator predates on the prey population decreases. Now the predator does not get the actual food, its share. So what happens, the predator population also decreases. It's a cycle in which the predator increases at one point of time and the prey increases at the other point of time. You can see in the figure. And one point you have the predator domination, one point you have the prey domination, then there is a kind of decline, they'll reach kind of an equilibrium, again the system repeats. This is what nature tells us. So we try to kind of try to understand the whole things in terms of mathematics. So the important concept to understand it mathematically is what is called as a functional response. What is functional response? It is like, to put it in a very simple terms, the number of prey that the predator encounters at any given point of time, depending on the density of the prey. It's like It's like if suppose X is a predator, how many prey can it see? That is what we call it as a, how it responds. And because we are mathematicians, what do we say? Functionally. We always use the word function. So how functionally the predator responds towards the prey is called as a functional response. Okay, so it's like number of prey encountered in a given unit time per predator, by one predator. So what are the different kinds of functional response that we see? This all has come from nature. So what is that first one? First one is called as a type 1 functional response. It's like it does not bother the handling time or searching time. It's like as the density of the prey I have, it just linearly increases. The predator keeps on attacking. One simple example can be, you can see here this European and this vole. So this is an example, though I see from the internet, this is the figure. I can see it takes some time, but usually ideally in type 1 response, what is the assumption which we make? The predator directly feeds on the prey. Actually the handling time is almost negligible. That we call it as a type 1 response. What is a type 2 response? Type 2 response is more realistic, and by the way, this is coined by Holing. So very great ecologist. So what he said was type 2 response. Yes, of course, when the predator is hungry, it's like it can be applied to real life also. How many samosas can we eat? Let us say we start initially, okay, we just start taking samosas, but we'll reach a saturation where beyond that, though I have 10 samosas before me, I'm not able to eat it because there is an upper limit. There is a threshold value. The predator gets satiated with the food that we have. So there is initially an increase in the intake of the prey, and after a certain time, you have a constant behavior happening. That we call it as type 2 response. This is one example of what we see in the nature, in the ecological studies. This has been observed. Then we have a very interesting function response called as type 3 response. What happens in type 3 response is that initially the predator is not able to detect the prey. It can be due to the low density of the prey. So what happens is the predator, it's a kind of an accelerating, okay, previously it's kind of an decelerating functional response because there is a decrease in the top. Here it's initially there is a kind of a decrease and increase. So we call it as an accelerating functional response. Okay, what happens is when the prey is very low, when the prey population is very low, the predator is actually not able to detect the prey. So what it does is it switches. So it switches to alternate prey. That is one behavior which we can observe. And also what happens is in this time, what we call it as a learning behavior of the predator. There is a kind of learning behavior that the predator observes of the prey. So it's like starting time. It's like when you have an Olympics, you have the heats first, then you have the actual race, right? So before actually it predates, what happens? It runs the heat. So it kind of observes what happens it observes the prey behavior. It's called as learning behavior. Then it starts attacking. So this is what nature tells us. So it is like, maybe I should say the ecology speaks about this. So some example you can see here, okay. This is an example, you can see this bird and you can see this larva. Though in the figure it is very huge, but actually when the bird sees, it is very small for it, so it cannot actually catch the larvae. So it kind of spends some time and finally gets the larvae. So now mathematicians take over. So whatever we have seen in ecology, now we try to put it in mathematics. So what is that first thing is, I said type 1 response. So with respect to predator density, the predation happens. There is a kind of a linear increase. And here, as I said, initially it zooms up, then what happens? It decreases, or it reaches a constancy where you have the line to be almost to be constant. Then here you see initially there is a kind of a little low increase, then it picks up, then again it becomes constant. If you see the predation rate, for type 1 response, the predation is almost more or less constant. Type 2, the predation initially is very high and it decreases. For type 3, what happens? Initially the predation is low, then it zooms up, then again it comes down. So to sum up, what are this type 1, type 2 and type 3 response? We can see here. As the prey increases, predator takes more prey. But how does the predator react towards the prey is the question. In case of type 1 response, it's a linear reaction. In case of type 2, it's decreasing rate, you can see it decreases and becomes constant. In case of type 3, we have kind of a sine function. It's called sigmoidal function, sine function. Initially, there is a kind of a not so fast behavior, then it picks up, then again it becomes constant, okay. So these are the different kinds of response. We have formulas for this also, how functionally. So what is this called as? functionally predator response towards the prey. We have one more response called as numerical response, which I am not going to deal with. But what is numerical response? How much prey can I encounter? Literally I count. This is something like a qualitative feature. What is numerical response? Something like a quantitative feature. Basing on the size, literally the size of the prey, how the predator responds. That is what is called as numerical response. So now this is one part. So this is one part of motivation why we are studying predator-prey systems. There is also one interesting application in biological conservation. So what has happened is, this is called as diversionary feeding, which is used in wildlife conservation. What happens is, I want to protect a species. So it has a predator which feeds on that. So why not provide this species, this predator species, with some other additional food? It's in the sense that you are actually supplementing the predator with some additional food. So what happens thereby? Here you can see, you distract the predator from predating upon the target species, thereby you conserve the target species. So this is called as biological conservation. Why am I calling it biological conservation? Because I'm conserving some species. So what is the motivation? Again, as we said, every research work gains a lot of credibility or value when you actually derive from the nature or maybe from the epidemiology. The data-driven research is the order of the day. Okay. So what happened in this experiment? They have this grouse chicks, the way they are this lagomorph, how they kind of a predator predates these grouse chicks. They have provided it with an alternate food. So you can see here, these are owls which actually attacked grouse chicks. Okay, that photo is not there. So what these people have done in Scotland is, they have provided an alternate food to this lagomorph, what's called owls. So the rate at which this actually attacked the grouse chicks decreased because they are fed with the alternate prey. And also we have one more application for the provision of additional food. What is that in case of biocontrol? What happens? Chemical control has been happening. We actually, to control the pest, we give the insecticides and pesticides. But what happens is, it is environment hazardous because of two reasons. First thing is, because of the toxins, maybe the farmer's health get affected. Second observation is that the fertility of the soil will starts to degrade when you supply when you do this insecticides and pesticides. So what is that people have done is like biocontrol studies, as I said. So what is this biocontrol studies is, you want to control the pest. So what is that you do is, you provide a predator, it's a kind of a natural enemy which feeds on the pest. I'll show you one example. You have here Courtney cushiony scale. This larva is actually eaten by ladybird beetle. Okay, so in the way this is a pest actually, which is actually hazardous to the agriculture farm. So this is an example. You can see, maybe I don't know whether you are able to see this small pest insects. So you have this predator which is feeding on this prey. Okay. So next, what we can do is, one more motivation is observed in ecological studies is that when you supply an additional food or alternate food to this predator, then what happens? Its longevity and also its fecundity increases. Thereby the population of these predators increases, and the rate of predation, the rate of attack also increases. So giving alternate food is a very ideal thing. So this is actually supported by these references, where the predator behavior gets enhanced. This is what is observed when you provide the alternate food in these studies. And also one last maybe, so because before I start a study, I really want to convince myself more than anyone else that what I am doing is sensible and what I am doing is meaningful. So first we should actually see what motivates us to go to these studies. So one last observation which I have is, in nature again this predator prey, when the prey is more, we have one more behavior, very interesting behavior called as inhibitory effect of the prey. What is inhibitory effect? It's called a group defense. So when the prey is more, the predator, actually they kind of switch the role. The prey becomes the predator in a way. In the sense, because of the group defense or maybe group toxicity it's called. Suppose a predator attacks a plant, okay, which is its target prey. There are a group of plants, then it releases some toxins which are actually hazardous to the predator. So this is called as a group defense or group toxicity. The name is actually called as inhibitory effect. As I tell my students always, you understand by the name. What do you mean by inhibitory effect? The prey inhibits the predator from attacking it. That is how I understand what is an inhibitory effect. So how do you remember type 4 response? It's like the prey is actually inhibiting the predator to attack it. So that's how I call it as an inhibitory effect, right? So what are the, like you can see, I've given some examples. Muskox, fending of wolves in herds, and also we have spider mice producing complex interference. So what do you observe? See, actually this is the predator which is predating that. What happens? In a group, this actually becomes a predator and this becomes the prey. Kind of a switching thing that happens. This is what is called as an inhibitory effect. Okay, this is what nature tells me. Now what should we do as a mathematician? Because yesterday one student was asking me, sir, how do you get these models? Because I am seeing a lot of models, but how do you actually come to the model? So let me go from the basics, maybe derive the model, and maybe quickly I will go to the insights, applications of it. So first thing is, now as Professor Sheshar was telling, all mathematical models are wrong. Sir, I want to change the statement, sir. All mathematical models are insufficient. Just that some models are insufficient than others. So I would not say it is wrong, just that I would say we don't have the capabilities to completely capture the whole thing. So I would say now people may ask, okay, delta t is like the total time. I'm just splitting it into the search time and handling time. Now this can be questioned. I can have so many other times. Yes, but somewhere we have to start, right? So somewhere I will start quantifying the things rather than just trying to capture all the qualitative features. So I will say total time is broadly I will say total time is the search time and the handling time. So now how do we measure this handling time? Okay, so handling time of the prey by the predator. So let us simply logically think, how do I try to understand what is this search time? So sorry, handling time. So how do I do handling time? It is, I can split it as handling time of one prey into total number of prey caught, right? Simply, it is just the handling time of one prey into total number of prey caught. When I multiply with total number of prey caught into the handling time of one prey, what is that I get? I get the total handling time. So the issue is, how do I get the total handling time? Okay, so total number of prey caught. So before that, if I want to get the total handling time, I have to understand what is the total number of prey caught. And we can easily see that the total number of prey caught is proportional to the search time and the prey. That's a simple observation we can do. Say if I want to measure how many prey was caught, I need to search for the prey, and also it depends on the density of the prey. But the beautiful thing is, we have a constant of the proportionality which happens. This is proportional to this. This constant actually plays a very crucial role in determining the different kinds of problems what we do. What is this constant? It's called a proportionality constant. It is nothing but the catchability of the prey. How many prey can the predator catch? Okay, I mean, like, what are the prey caught by the predator? So what I do is, I actually coin it as E1 by Bn square plus 1. Okay, this is where the interesting part of our research lies. So E1 by Bn square plus 1, I am calling B to be the inhibitory effect. So suppose if B is equal to 0, what happens? I just get only E1, which is nothing but the search rate of the predator per unit prey. If I have B to be more, what happens? What is that I want to capture? This is how the mathematics go. I want to capture that predator attack rate should decrease with the inhibitory effect. Am I right? Right. So the predator, the rate at which the predator attacks the prey should decrease with the prey density. Do you all agree with that? Right. So what I do is, I put it as E1 by Bn square plus 1. So when B equal to 0, what happens? I just get E1. This is nothing but the catchability. This is nothing but the catchability of the prey. So if B is more, if the inhibitory effect is more, then what happens? The catchability of the prey decreases. You are able to understand, right? So the number of prey caught decreases with respect to the inhibitory effect of the prey. And next thing is, if you want to get type 2 response, this type 4 is kind of a generalized version of type 2 response. Type 3, I just call it as E1 into N. Why? Because at low density, my predator's attack rate is less. At high density, the predator attack rate is more. So E1 into N. So if density is more, what happens? Attack rate is more. So this is one single term, because always when we send for publication, my little understanding, first people will ask is, how do you get the model? Okay, once the people are convinced, the reviewers are convinced with the model, then what happens? Maybe the further things they may look at. When your model itself, you have some confusions, then maybe I don't know, where should we go ahead? because we want to kind of get it to the type 4 response format, because Holing has said we have 4 types. There are that functional response, this whatever we derive should fit into that functional form. Then only it makes sense. That is why we actually tried with different things, but how do I actually get to the fit to the functional response form? Okay, so I mean you have known the different kinds of response. So okay, I'll just get back to you after the class. So functional response, we want to fit into a standard, say like whatever we develop, it has to fit into one of the 4 functional response, type 1, type 2, type 3, type 4. So owing to that, we have got this bn square plus 1. Right. So now once this is done, the major step is done, then it's just a quickly kind of going through the model. So what we get is delta Tn is nothing but handling time into the, handling time of one prey into the total number of prey caught. So now maybe I'll just be a little quick. So with that basic, because I wanted to spend some time so that you understand how the model is actually coming about. So what is your functional response? It is nothing but the number of prey encountered per unit time, right? So what is this total number of prey caught by total time? Gives you per unit time how much prey did the predator encounter. That's all is this equation. So then I put my number of prey caught, and total time is nothing but the search time plus handling time. We can have so many other times, that is how the research takes over. So right, okay, then maybe I will skip these slides because I do some kind of maybe manipulation or jugglery. And finally what is that we get? We get f of n to be of this form. In that, what is that I do? I call C to be 1 by h1 and I denote A to be 1 by E1 h1. So my functional response take this form. A typical, Ram Singh sir, so a typical functional response of type 4 should be of this form. That is the reason why I have chosen E1 by Bn square plus 1, because initially I started with E1 by Bn plus 1. Why not Bnq plus 1? That was what your question is, if I understand. So because I want it to of this form, because I want mathematically this actually describes the type 4 response, so I had no choice but I have to fit that, at the same time capturing the inhibitory effect. So that is why I chose this form. Okay. So now what happens? This all I think all of you know it. Predator prey. I think yesterday sir has given, Sheshya sir has given why do we need predator prey equations. So this is a logistic growth. Exponential growth is meaningless. So this is a logistic growth. There is a kind of predation that is happening. So the predator population increases logistically in the absence of prey. Then I have a kind of predation happening. This is, I call it as a consumption. This is, I call it as a birth rate. Then this is the death rate of predators in the absence of the prey. Okay. And why the consumption rate and the birth rate are different? Because whatever we consumed may not get reproduced. Only part of it will be, part of the energy will be used for the birth rate, right? So that is why we have to keep a epsilon 1 term. And what is this f of n? F of n is nothing but the functional response. This is how you get multiple models. Models with type 1 response, models with type 2 response, models with type 3, and models with type 4 response. This is the kind of major things what we do in ecology, especially in the predator-prey models, right? So this is the equation. From here, maybe I think most of you know. I will not kind of routinely tell about what are the equilibrium points, what are the bifurcations we do, because everyone, especially I think all the participants know this stuff. Okay, so R and K represent the intrinsic growth rate, M represents the death rate, then B represents the inhibitory effect, and also the parameters C and A stand for the half rate of predation and half saturation value. Okay, if anyone has doubts, I will tell back to you because I want to go through my lecture. And the end, if we have time, I will tell you why we are calling it half saturation, why we are calling it maximum rate of consumption or predation. Okay, G denotes the growth rate of the prey. I told, right, once you do that whole calculation, you will understand this. So now I non-dimensionalize. Everyone knows, right? Why do we non-dimensionalize? We non-dimensionalize because we want to reduce the number of parameters from the main equation, and this is very easy to solve. So we non-dimensionalize the system, and of course we can have this. These are the predator-prey isoclines. I hope everyone knows this, so I'm just kind of quickly going through this. Then what is the interesting thing is, here this is the prey isocline, y equal to g of x. It exhibits 4 kind of behaviors. When we plot and see it, I have a crust and trough here. Here maybe I have a crust. These two are decreasing kind of a prey behavior. Multiple behaviors happen. It happens because of the derivative function. Because g of x, how do I study the behavior of the function? If I study the derivative, I know whether it has a maximum or a minimum. It has a crust or a trough, g prime of x if I take. What are the points at which g prime of x equals 0? It gives me the crust maximum as well as the trough minimum. So these are the 4 behaviors that get exhibited. Okay, these are the cases, these are the behaviors. Taking the discriminant condition and all those conditions. So we see it has a crust and trough in the first case. Second case, it has a crust. And third case and fourth cases, it is monotonically decreasing function. Okay, so now this all people know, maybe for students' sake, I can say, why do we need to study equilibrium points? All those things I'm not going to go, because equilibrium point, as soon as you reach, you become stable. So that is what is the law of nature. Everyone wants to be stable. Who wants to be unstable? Okay, so you understand that when we come to the equilibrium point, that is the point where you get the constant behavior. So that is how, so why do we study equilibriums? Because that is how the nature is. That is the law of the nature. So we cannot avoid the law of the nature. That's how humans are also. So we study these equilibrium points. Only thing is, it exhibits different behaviors. Equilibrium point, asymptotically we reach it, but we want to reach it in the finite time. That is optimal control studies which we have planned to do. So what are the different behaviors which we do is that, which we observe is that this is a saddle behavior, right? So one direction, I have a stable node coming. Other direction, I have the nodes repelling. It's something like a horse saddle, you understand, right? Horse saddle, when you sit on the saddle. One direction, I have a stability happening. Other direction, I have a instability happening. Something like, that is why the name saddle comes over here. Then you have this kind of a stable node. Everything comes and merges to that. Here the equilibrium point is 0, 0. We are speaking about 0, 0. Then you have a spiral behavior. This is very interesting behavior. You have a periodic behavior. It sends the same points, the same behavior. You start at somewhere the initial point, you come to this limit cycle and you keep oscillating, not oscillating, you keep kind of cycling around this equilibrium point 0, 0. These are the different behaviors exhibited. So these are the equilibrium points, okay? We have the axial equilibrium. Sorry, this is the trivial equilibrium, axial equilibrium. We have two interior equilibrium happening for the initial system. So these are the transcritical bifurcation. I understand bifurcation, I assume that some of you know bifurcation. So what is a bifurcation? It is exchange of stability. So the equilibrium point can be either stable, unstable, spiral, or it can kind of have a limit cycle. Now what is that I'm showing here? Here I'm showing that it undergoes what is called as a transcritical bifurcation. What is bifurcation? There's a kind of change happening, or there's kind of separation happening. What do you mean by transcritical bifurcation? Initially gamma 0, the axial equilibrium was stable. When as soon as I have the birth of interior equilibrium, it exchanges its stability with gamma 0. So that's what I call it as a transcritical bifurcation, wherein exchange of stability is happening. Okay, I have two interior equilibrium births, so I have two transcritical bifurcations happening. And one more is very interesting, Hop bifurcation, I think you know. So Hop bifurcation is where it gives rise to a birth of a limit cycle. Okay, so we have the birth of a limit cycle also happening here because of the Hop bifurcation. Maybe I'll just take a minute to explain what is Hop bifurcation, which is very interesting. So suppose I change a parameter. Okay, let me call a parameter mu. So in my equation, I'm changing my parameter. Then what happens when I'm coming this way? There is a stability of an equilibrium. So this is my, let us say, phase portrait. I have this equilibrium, some, let us say, x1, y1. I have this equilibrium. So what is happening when I'm here, the equilibrium is stable. So wherever I start my initial point x0, y0, and I try to reach, what happens? Whichever way I come to my equilibrium point. So at, let us say, some mu equal to mu naught, the bifurcation happens. That is the break point or the bifurcation point. This is where exactly bifurcation happens. This is for all mu less than mu naught. I have the equilibrium point x1, y1 to be stable. Now as soon as the bifurcation happens here, then when I come for mu greater than mu naught, what happens? The equilibrium point is unstable. So when the equilibrium point is unstable, what happens? This kinds of pushes out everything. You're able to get, right? So whatever is there, whatever solution comes to it, it just pushes out because it is unstable equilibrium point. Now suppose somewhere in the phase space I'm starting at some, let us say x01, y01. This is some other initial point with which I'm starting my trajectory. Then what happens? This trajectory cannot cut itself. I hope because of the uniqueness of solutions, the trajectory cannot cut itself. So what is happening, if you carefully observe, what is happening is that I have one solution is coming like this, and from inside I have solution pushing this way. From one direction I'm having the solution coming this way because the phase space is bounded. That is one assumption which we make. So the solution is coming here like this, and the solution is going like this. So what happens in the process? You have a birth of a limit cycle. So wherever what happens in the process, I start from here, I come and fall on this limit cycle because inside I get pushed out, outside I get pushed in. So I have a limit cycle which is being formed. That is what is the cycle I showed you in the phase portraits. So many people just ask me, what is a limit cycle? So what is a limit cycle? You have birth of a periodic cycle happening in the process. So what happens is, how bifurcation happens at mu equal to mu naught. for mu greater than mu naught, what happens? We have a birth of a limit cycle. So many misconceptions is that the limit cycle is formed at mu equal to mu naught, which is wrong. Limit cycle is not formed at mu equal to mu naught. Mu equal to mu naught is a bifurcation point. Limit cycle happens after the bifurcation because of the bifurcation. So that is what is called as an Hopf bifurcation. Okay, maybe so much about this. So let me just quickly go to the bifurcation. So how do I get the bifurcation diagram? I base on these conditions, 3 conditions basically: existence, stability of the equilibrium points, as well as occurrence of Hopf bifurcation. So these conditions can be further subdivided basing on the behavior of the pre-isocycline. Due to lack of time, actually I have not explained this bifurcation diagram. It is very interesting and challenging. So what happens is I get 6 regions in fact. This entire thing is region 1, region 2, region 3, region 4, region 5, and somewhere we have region 6. Okay, we have kind of classified the bifurcation is with respect to the inhibitory effect omega and with respect to the carrying capacity gamma. So what we observed in this region is there is no interior equilibrium point existence. In this region, maybe the interior equilibrium point 1 exists. In this region, maybe interior equilibrium point 2 exists. In this region, this is the Hopf bifurcation curve. This is the Hopf bifurcation curve. So as soon as I cross this Hopf bifurcation curve, what happens? My interior point may become unstable. I may have the birth of limit cycle. So this is how I kind of qualitatively, maybe it may be a little oxymoron, qualitatively I quantify the system. Okay, so this is what I have with respect to the omega and gamma. This is the bifurcation diagram. So maybe I'll just initially say that in this region, quickly maybe I'll just go to this. In this region, what happens is we don't have birth of interior equilibrium point. We have 0, 0 and gamma 0. Only the axial equilibrium points existing in this region. That is what is the behavior initial system is exhibiting. Then in this region, maybe I don't have the birth of the second interior equilibrium point. In this region, maybe we have all interior equilibrium points behaving. So this is actually the kind of a summary of the bifurcation diagram. This is actually the qualitative summary of the bifurcation diagram. So what is that each equilibrium point, E0, E1, E2, E3? So I can see what are the different behaviors exhibited in each of these regions. This is what we call it as a bifurcation analysis of a system, right? So now maybe then what we do is, this model I will not take time. So how do we kind of provide additional food? This is where the means like we have to kind of intelligently try and develop the model. We have search time, we have the handling time. But when I'm providing an additional food, because what does the nature say? The ecological experiments, when you provide the additional food, you have some kind of interesting dynamics happening. The predator attack rate may increase, or some studies said that predator attack rate may also decrease. So we want to mathematically justify ecological studies, ecological experiments, what was happening. So what do I do here is, I keep 2 handling times. The first handling time is with respect to the prey. What is the second handling time? The second handling time is with respect to the additional food. I think some of you are working, actually I'm looking forward for your paper presentations. So I want to see how you have developed the model. So this is how I have developed the model. So then again the same process, only thing is delta Tn, of course you know, already I have explained. So delta Ta may change little bit. Okay, one change here is delta Ta. Okay, one thing is, how do I get delta Ta? What is delta Ta? Handling time of one additional food into total additional food encounter. But only thing is, the additional food, we are not calling it dynamic. It's not a prey by itself, it's a static food which we are giving. So there is nothing like an inhibitory effect exhibited by the additional food, because it's a static food that I'm giving. It does not grow with time. It's just something like a maize or corn or maybe some kind of roots which we give, okay, root plants which the predator eats. So there's nothing like a behavior or growth behavior for the additional food what we are giving. So the search rate I am just calling E2, but not E2 by Bn square plus 1. This is one place which we need to understand. In the previous case I called it E1 by Bn square plus 1. Here I am calling it E2, not just E2 by Bn square plus 1, because it is a static additional food that I am giving. So then you can quickly get what is this f of n, the functional response of the predator with respect to the target prey. It comes out to be maybe, okay, it comes out to be something like this. Again, this is nothing but the functional response with respect to the additional food that I provide. Okay, maybe quickly. So this will be the final shape of f of n. This will be the final shape of g of a. So now what happens to the predator-prey model? How do you get the new model? Here, because here the target prey is getting affected because of the predator. But how does the predator change? The predator changes behavior with respect to the growth rate of the predator is due to the target prey, as well as there is a contribution because of the additional food. This is how we vary the model. because there is a birth rate of the predator due to intake of the target prey, and also there is a birth rate of the predator due to intake of the additional food. You are able to get it. So that is how I get this new model. Then I substitute the functional response and everything. So again, one interesting thing is, again, as I always keep telling about quantity and quality, ultimately in the studies, we call this two terms, alpha and also, okay, I'll just come to there. Okay, this is the model again. You have G to be the growth rate. I want to discuss about these two terms because this I can call it as a control parameters. Why am I calling it a control parameters? At the end, it becomes clear at the end of the study. So what is alpha? Alpha is nothing but epsilon 1 by h1. Alpha is nothing but epsilon 1 by h1 by epsilon 2 by h2. It's something like g1 by g2. Okay. So what is g1? Growth rate of the predator while consuming the target prey. What is g2? Growth rate of the predator while consuming the additional food. So my alpha is in a way telling the quality of the kind of food that it takes, because the first one is telling you it's a kind of a relative quality, maybe you can say. It's a relative quality because the numerator I have the growth rate of the target prey and the denominator I have the growth rate of the additional food. So in a way I try to quantify, means like whatever is that, it's like I'm calling it a quality because I'm measuring the growth rates. So basing on the quality, now real world people may ask, what do you mean? Because mathematics has to make sense with the real world. What do you mean by quality of additional food? People may ask this question. So first thing is, it is the calorific value of the additional food that we provide. That can be one instance. What do you mean by quality? What do you mean by quantity of additional food? The quantity of additional food is nothing but then literally the number of grams of additional food you give or the kilograms of additional food you give. That is nothing but the quantity. And eta A actually denotes the effectual value or effectual additional food which the prey can encounter, so which the predator can encounter. Okay, now we go to the new model. Okay, so this is how the new model looks like. And alpha and xi, here you have alpha and xi. Alpha, maybe after the presentation I'll just take your question at the end because I'm running short. I'll just quickly complete this and again I take your question. So alpha and xi can be the quality and quantity of additional food. So when I keep alpha equal to 0, what happens? It becomes to the original model. When there is no additional food, what should happen? Mathematicians are, how they do? They develop always a general model, right? When you come to specific, because what do we do? Mathematical induction, we start from n equal to 2 and we prove for n equal to m. That is what we do in mathematical modeling because mathematicians does not change. Okay, so what do? We have added something to the model. So when we remove something from the model, it should become to the original model. So the generalized model should cover the specific model also. So what we do is, when alpha and xi are the new quantities, when we make alpha or xi equal to 0, this entire thing becomes to the original model. So the original model, I'm calling it to be the initial model, and this I'm calling it to be the additional food provided model. So what happens to the consequence? We have all this, again, this inhibitory effect can be understood because of omega, and carrying capacity can be understood because of gamma. So okay, what I said here is an interesting observation. Beta, delta and gamma, the death rate, birth rate and the carrying capacity can be considered to be the echo parameters in the system is actually providing us. But what is alpha and xi? Alpha and xi are nothing but the quality and quantity. Because we are providing in quality and quantity, we can control quality and quantity of food that we provide. So I can call them as a control parameters. Because birth rate and death rate and carrying capacity, in a way we cannot control. Maybe in lab you can say you replicate the conditions, but usually the ecosystem gives us. The easiest thing to control is quality and quantity of additional food rather than the birth rate, death rate of the prey, because we have to do some fundamental changes in the ecosystem. But this is, the food we kind of give to the ecosystem can always be controlled by us. So I'm calling this alpha and xi to be the control parameters, right? So now I see this isoclines. Okay, all these behaviors happen. I'll just quickly, because these are the new interior equilibrium points, and this is the, again I have this transcriptal bifurcation, all those things happening. So what we have done is, in the region 1, if you remember the diagram, okay, I'll again get back to the RAM. In the region 1, when we provide additional food in the region 1 means under the condition 1, we had 6 conditions, right? If you recollect, in the bifurcation diagram, we had 6 conditions. So under condition 1 of the initial system, when we provide additional food, what are the qualitative features exhibited? That is what is this paper which I said, Springer dynamic equations and differential equations in dynamical systems. That is where this work has been communicated and it got published recently. Now what I am going to speak, okay, maybe I should rephrase. I am speaking about both what my students Aditya and Murari have done. So this is the work of both of theirs. So Okay, so region 1 Aditya has done, and he has led the way for Murari to do all the 5 regions, remaining 5 regions to actually work out. But what happens is, the first step is the most toughest step. Once you take the first step, second step also becomes easier. So the first step has become an MPhil, second step has become a dissertation. So that is the difference. So the intensity of the work kind of comes down when you already have something to start with, okay? So right, so we try to see for research, we try to see for the regions 2 to 6. So due to lack of time, what happens in the initial system, I just want to focus. In the initial system, what happens? Okay, this is my 0, 0 equilibrium. This is my gamma 0 equilibrium. These two are interior equilibriums. So what is happening in the initial system is, I don't have birth of interior equilibrium 2. And what is happening for the interior equilibrium? Both of them are saddle. And what is happening to the interior equilibrium 1? They are exhibiting limit cycles, and also they are globally asymptotically stable limit cycles. This is what is happening to the initial system. Now let us see when I provide additional food. Okay, maybe one graph I'll explain, and then I'll try to wind up. So what is happening here in the additional food provided system is, now on this line alpha equal to 0. Alpha equal to 0, actually I'm on the initial system. So I start somewhere at alpha, and I increase. This is the quality of additional food. This is the quantity of additional food. So I increase the quantity. Then what happens? It cuts this transcriptal bifurcation curve. It cuts this kind of a one pre-elimination curve. It cuts this Hopf bifurcation curve. So we have interesting qualitative features happening. We have birth of maybe interior equilibrium 3. We can make E2 to be unstable. All those things we can happen. Okay, this is in region condition 4.1. I can see in, so these are the isoclines. Condition 4.2 also I have multiple behaviors happening. Okay, so these are the isoclines in that system. So what is that happening in each of the regions? I have said A1 to A8 and B1 to B7. So we have these different behaviors. Okay, so now my request is, compare with the initial system what behaviors it exhibited, and compare with the additional food system what behaviors did this exhibit. So all of you can easily see that I have so many other features which are happening when I provide additional food, which was not happening in the initial system. I hope everyone get that point, right? So this is the beauty of our study, and maybe this is in region 5. Okay, these are some of the observations. Maybe what is that? Okay, I'll come back to this slide again. So what is that happening? In the initial system, what did we observe? The 0, 0 equilibrium point was stable, was saddle, E1 was saddle, E2 was unstable, exhibiting globally asymptotically limit cycle. So now what happened when we provide additional food? What did we observe is, we can make what was saddle can be made to be unstable. What was E1 again saddle can be made to be stable. E2 star was stable, it can be made to be non-existence. What can we do? E3 star, which was not at all there, can be got into existence with saddle nature. So these are the kind of qualitative things that can happen. So, and also in fact very interesting thing, in the region 4, the initial system did not even have a homoclinic orbit. So we can in fact get the birth of a homoclinic orbit. It's a very interesting qualitative feature. I hope people know that, participants at least will know that. So we have a homoclinic orbit, and we also have a heteroclinic orbit. Okay, something to do with the kind of a periodic nature. So we have some very interesting things happening. So ecosystem, when we say we try to kind of quantify it, we have so many very interesting behaviors which we can observe when we actually go to the study. So this area really fascinates me because we are studying nature, and we are in fact applying mathematics to understand the nature. And of course it has got tremendous applications also. Then when I come, I will tell you. Okay. So again the same thing in Eve. So now that you have got an idea, maybe I will not take time to this all features. But one interesting thing which I wanted to share was, so what can we do with additional food? This is why I'm calling it controlling the system. Suppose if I want to reach the point x bar, y bar, wherever x naught, y naught, I start somewhere at the initial point. My trajectory should kind of reach to x bar, y bar. So what do? That is, I solve these two equations. These are kind of two system of equations. What are the unknowns? The unknowns are only alpha and xi. Why? Because I know the target state x bar, y bar where I have to reach. What are the other three things I have here unknowns? Beta, delta, and gamma, maybe somewhere gamma comes. Okay. Beta, delta, and gamma are the echo parameters, which I already know. X bar, y bar, I know. So what is that unknown? The unknown is, you don't know alpha and xi. So you can find out the quantity of additional food and the quality of additional food that I provide, so that I can reach x bar, y bar. So it is something like when you do mathematics, you should always have that thin line, because we feel like we are controlling nature. Because I am making my system to come to my point, right? That is the beauty of a study. Okay. So I am making my system. Suppose I want the system to come to a specific state. I'll ensure that I'll control my predator, sorry, I'll control my quality and quantity of additional food such a way that I'll reach my X bar, Y bar. That is something fascinating. But of course, nature has its own course. So, but at least on board, okay, at least mathematically we can say that using these control parameters, we are able to reach X bar, Y bar. Okay, either I can, no, it's not moving. Now it moves, okay. Can just, because I'm running short of time, or can just go to the next slide? I'll tell you, okay. Right, so I can either reach it asymptotically or I will reach it via a limit cycle. Okay, now this is what is the study, okay, it works now? Okay, so that is one thing. So, yeah, so what are the biological insights that we get? Okay, because study has been done, but until you apply to nature, because nature has motivated you, you have to give back to the nature. What you observe, it's like, means like people say Prasad and Naivedyan cycle. So something like we get that and we again get back to the nature. So what is this biological insight that we get? Okay, first thing is with the provision of additional food of suitable choice, I mean a control with a given right choice of quality and quantity of additional food, we can steer the system. I already told you, if I want to take the system to X bar, Y bar, I just need to choose a rightful alpha and xi. So I can steer the system to a specific equilibrium point. That is one thing. And second thing, that's what I think I was saying, where I can make it high predator, low prey, or I can make it high prey, low predator. You're able to understand. So what are this? Right, okay, that's what, that eliminate. So what happens, it can be interesting thing. I can make the system to go to gamma 0, or I can make the system go to something like 0 comma kappa. So I can make the system to be prey dominated, or I can make the system to be predator dominated. So all these kind of features we observe. So what is this application of this entire studies? This application of this entire studies is in biological conservation. Either I can conserve the predator prey, or I can remove the prey totally, which has got application in biocontrol. What is that I do in biocontrol? I want to remove my pest totally. I want to in fact eradicate my pest. So what should I do? By mathematics, I should ensure that system reaches to beta comma 0. So I should make it predator dominated rather than prey dominated. Then what happens? The prey gets totally eradicated. So this is what are the applications of this study. One is in biological conservation. Biological conservation, I want both species to be stable. So I have to make the interior equilibrium, which is x1, y1, to be stable. So x1 predator population, y1 prey population remains stable. So I can actually biologically conserve the system. In fact, I can biologically control the system. This is by providing the additional food. And how do I do additional food? I control the additional food with the quality and quantity parameters. So in short, this is the kind of work which we have been doing. An arbitrary choice, again, why is that we see the negative effects? Because quality also, again we can, because I don't have time, quality also can be classified into two things. One is high quality, high nutritive value additional food. Other one is low nutritive value additional food. So when you provide, how much time do I? You're done? Okay, I'm done, sorry. Okay, so maybe just 2 minutes and I will wind up my talk. So what is low quality additional food? In the sense that it actually, gives a negative growth rate. If you can provide the food that is not actually conducive for the predator, then it becomes a low quality additional food. So what is that I say here is, an arbitrary choice of additional food can result in completely opposite results. So you have to be very careful what kind of, not just the quality and quantity, but always you should ensure that you try to provide a high quality additional food, but not low quality additional food, because you are getting the opposite results. Okay. So these are some other regions, maybe due to lack of time. So I have shown you only 4 and 5, but we have a lot of qualitative features. This is in region 2 and 3. These are the additional features, and also these regions 4, 5, and 6. We have all this. Really means like when I read the paper, sometimes I really get fascinated with the kind of qualitative features exhibited by dynamical systems. It's like uses so many behaviors. Actually, you can see if you really count, we have almost some 4 to 5 behaviors exhibited. And it is our insufficiency that I am not able to find some more behaviors, because I am yet to study some more nonlinear dynamical systems. There are so many other behaviors which we can get, qualitative behaviors which we can get from dynamical systems also. So I was working with Professor P.D.N. Srinivasu, who introduced me to this area, and also Professor Ratish sir. So we are taking it further ahead with the control. What was happening, everything was, because with respect to the infinite, what should I say, it's because of the asymptotics, okay, that's the right word. So asymptotics, because I reach everything asymptotically stable. So in infinite time, actually I'm reaching my point. But if I have to reach from x0, y0, x bar, y bar in a finite time, that is what is called as an, and to the finite path in the optimal time, in the optimal path, that is called as an optimal control studies. Okay, this is what maybe I can say brother Anant also is doing. So what my students have done, maybe I have put in a nutshell. Murari has, not Murari, Aditya has worked on type region 1, Murari has worked on region 2 to 6. Now what I think he is going to do is, he is going to study for time optimal control studies for this type 3 and type 4 response. Okay. So these are some of the references from which I have made this slide. Okay. So finally I dedicate this presentation at Swami's Lotus Feet, and I thank you for your patient listening. Okay. So though I know that I don't have time, but maybe can I take a quick question? Am I allowed? Yes, sir, I would really love your comments.
Well, thank you. It's a very nice combination of mathematics and biology. It's very interesting work. I just have some comments.
Yes, sir.
And one, when you put this alternate food, right, then there's a different direction that you can say that the predator has food preference.
Yes, sir.
And then you could have, instead of the approach that you can have a predator that switch. And
that's what type 3 I'm just trying to do.
But you have like, and switching might be tied into frequency or something like that. Okay, that which food is more available, but also, of course, it could be due to preference. The other thing is interesting is when you talk about these defenses from the predator, prey. There is a literature about plant defenses. And in fact, there is some of the people that are involved, you might all know all of them, Simon Levine, and there's also a guy, Fred Adler, and other people that have been writing about that. And there is an interesting strategy that is, if you are a plant, okay, then the question is, and this is not the way biology works, but this is a good way to talk about it, is you could have different kind of herbivores, and you might defend yourself by creating some sort of general defenses, general chemical defenses. That's one strategy. Of course, it has a cost to you. You might be able to reproduce less of. Or there might be some particular herbivore that is more focused on you, and the ones that survive is the plants that develop defense against a particular type of predators, not all herbivores. So that might be interesting to see whether being a generalist defense or being a specialized defense.
Maybe we need to have two equations together. One is generalist and one is
but
specialist.
This, under what conditions, which one might be the best strategy? And I don't know. And the last one, I talked to your student a little bit before your excellent lecture. And Michel de Lara has been looking at this problem, but from a different perspective. I forgot the exact terminology but essentially he's looking at the basis of attractions of the different equilibria, and you have multiple equilibria here. Yes. And the question is how to control the initial conditions so that you can reach the right equilibrium, which is might be complementary. So thank you. Okay, just three comments.
Okay. Go ahead, Tan. Maybe one quick question, maybe, and then I can.
Very nice talk, sir. This is not my question, it is my curiosity to know that you have used a non-dimensional technique. Why do you have used that technique? Yes.
Both ecology and epidemiology.
Yes.
Both places, because we reduce, already it is complex to a certain extent. So we try to, like, what is the worst complexity we can have, or what is the best complexity we can have. So we try to reduce the number of parameters, actually because we need to do bifurcation with multiple parameters. So we try to reduce a bit number of parameters so that this is little easy to handle.
You mean to say that just to simplify your problem and solve the, we have also used the non-dimensional technique, but in other models. Okay. As far as I know that we use non-dimensional things, For example, you have to applicable your going to apply your model in the very microscopic level and very macroscopic level, where the dimensions are not measured in the microscopic level when the because prey predator model is also holding also applying when the things are can't be seen by naked eyes. Because you are talking about the things which we tigers and goat and blah blah, blah any animals which can be seen by naked eyes. But there some type of system is also happening with the system when we can't see with naked eyes. So at this level, when you non-dimensional things, so you can use the non-dimensional technique, because at that level we are unable to measure the dimension. Sometimes, for example, I say that measure the depth of a sea, which is very difficult task to measure. So where do you measure that? That is the way of, it is my general discussion.
I understand.
So it is a true meaning of the non-dimensional things, because when we apply our model at macroscopic level as well as the microscopic levels, so we try to use the non-dimensional things so that this type of measuring problem can be avoided.
So like scaling and normalization, both the things.
Yes, yes. This is my.
Okay, I think we need to take a break now. So these are my standard announcements. So we'll meet after 15-20 minutes here, sir. So next we have, I also would like to thank my guide, my PhD guide, Professor Pallav Kumar Barua, sir. So because I think looks like my friend just let me, and also I want to thank my friend for giving this such cordial introduction. Okay, right, thank you. I told it at the last time.